First, I welcome everyone to the last webinar series of the disease resilient and energy efficient centralized air conditioning system. The last topic is very, very interesting. It's focused on refrigerant management for centralized air conditioning system. And we have some esteemed speakers lined up today. And I will introduce them as we go along. I will be hosting this webinar today. Before we go to the next part and start the webinar, I want to talk a little bit about the housekeeping. So we encourage all the participants to be interactive in this session. So please chat, put your comments in the chat box. You have access to open your mic and you can talk. But I would recommend you, to disrupt the flow. If you can put your questions on the chat box, please ensure that you have enough battery and you have your mic on mute, and I request only the speakers who is speaking to keep their video on and keep everybody else to keep their video off so that we can manage the bandwidth. Like I said, you can raise your hand if you have questions or put it on the chat box. And at the end of the webinar, we will send the feedback form, and we would request and encourage everyone to submit their feedback so that we can incorporate that in our future workshop and webinars. Well, with that, I start the webinar, and the first speaker of the day is Jinmiao Zhu. He is the energy specialist in the Asian Development Bank. Let me talk briefly about his background. So Mr. Zhu has more than 16 years of experience in the energy field. He is responsible for work related to carbon capture, utilization, and storage in the energy sector group of the Sustainable Development and Climate Change Department of Asian Development Bank, ADB. He also administers several regional technical assistance projects focused on CCUS, low carbon energy technology, roadmaps, and advanced centralized air conditioning systems. His expertise includes energy and environmental technologies, policies, and programs. He received BS in environmental engineering from North China Electric Power University in 2005 and MS in thermal engineering from Shanghai University in 2011. I welcome you, Jinmiao, for your welcome speech.
Thank you, Yash, for your kind introduction. Good morning, good afternoon, good evening, everyone. I'm Jinmiao, energy specialist of ADB and also project officer of the TA 6563 regional support to disease resilient and energy efficient air conditioning system in public buildings. Welcome to join this webinar series. In this month, we organized 3 webinars on subject of disease resilience, energy efficiency, and smart and automatic control in centralized air conditioning system. We introduced many emerging technologies and shared several study cases and regulations relevant to indoor air quality and energy saving. Today, we will have the last episode of this webinar series on refrigerant management for centralized air conditioning system. A centralized air conditioning system rely heavily on hydrofluorocarbons, a greenhouse gas potentially thousands of times more potent than carbon dioxide for cooling. Proper management of the hydrofluorocarbons through restriction and prohibition, development of substitutes, and harmonious treatment is critical to addressing greenhouse gas emission from the centralized air conditioning system. SDCC Energy Group of ADB and the Climate Change and Disaster Risk Management Division of ADB co-organized this webinar and invite professional experts to discuss life cycle management of fluorocarbons and introduce alternative refrigerants. So you know the recirculated air inside public buildings and other closed spaces can contribute to the spread of the novel coronavirus and the bacteria. Highlighting the role of the air conditioning system can play in the transmission of the COVID-19 and other airborne disease. In many developing member countries of ADB, such risk is higher because of inadequate hygiene standards, such as the use of old and inefficient conditioning equipment, lack of the regular maintenance, and large crowds in closed spaces. In addition to these explicit challenges, the refrigerant life cycle management, including refrigerant selection, using, and disposal, is also very crucial challenge for many developing countries. Refrigerant life cycle management is in centralized air conditioning system of public building is also an important research content in TA 6563. The awareness and the capacity of the government institutions, as well as the operators in public buildings, need improvement. Therefore, ADB proposed a knowledge support TA amounts to $1 million to help the DMCs to cope with the new challenges in CAC 16. ADB will import an India company to pilot their innovative technology solution in the centralized air conditioning system to address these challenges with grants up to $295,000. This is a regional TA, and the gained knowledge from this TA will be shared with the DMCs and accelerate economic recovery and go back to normal life. This webinar series is one of the important activity and the TA for knowledge sharing and awareness improving. ADB has been devoted to helping developing member countries addressing remains poverty and reducing inequality and tackling climate change, building climate and disease resilience, and enhancing environmental sustainability. My colleague of Climate Change and Disaster Risk Management Division are implementing a regional TA promoting life cycle management of fluorocarbons. This TA will help developing member countries to promote developing, manufacturing, and using climate-friendly refrigerants, and recovering, recycling, and destroying the discard fluorocarbons. The collaboration of two TAs is a good example of one ADB, and it will expand influence of the knowledge sharing and reach much more achievements. I hope the two TAs can improve the people understanding and awareness about refrigerants to choose refrigerants with the low GWP and reduce the greenhouse gas emissions through life cycle management. Finally, I wish this webinar a success. Thank you. Back to you, Yash.
Thank you, Janya, for the welcome speech and for introducing our TA 6563. Let me now start the first presentation. So today on the first presentation, I'm going to talk about the overview of refrigerant management for centralized air conditioning system. So let me just first start with the context in terms of why refrigerant management is important. Out of 101 solutions that a project drawdown has looked at, they have named refrigerant management as a #1 solution that will impact the climate change the most. And if it's applied well, and if we implement that solution, it has a potential to achieve 57.75 gigatons of CO2 equivalent reduction in the climate, and it can save a 629.25 billion US dollar lifetime net operational savings. So this is an important and very useful area where we need to look at to maximize and minimize the adverse climate impact. If you look at further, there are, out of the 17 SDGs, Sustainable Development Goals that has been proposed by UN Habitat, you can see that the refrigerant management would impact almost 7 of those directly, and those are the direct impact on the goals where you can have, and there will be many indirect impact of the refrigerant management that you get in the SCC. So what is a refrigerant management in centralized air conditioning system? So I've broken it down into 5 simple steps. So the first step is you have to reduce the capacity of centralized air conditioning system. So by designing our buildings in a way that you can reduce the capacity of the systems, that will reduce the cooling and heating capacity and the refrigerant use in the centralized air conditioning system. So that's the first step, how you can reduce the use of refrigerants in the centralized air conditioning systems. In the next step, you can look at climate friendly refrigerant. So when you are selecting the refrigerant in designing the equipment, the type of refrigerant is climate friendly refrigerant is what you would use in the system. You will see much more detailed presentation about these topics by 2 experts in the following after my presentation. The third component is how can we increase the efficiency of refrigeration system to again do the refrigerant management. The fourth and fifth is again very important so that we do a good maintenance of the refrigerant system or the centralized air conditioning system. And when I say maintenance, I mean, the leak detection and repair, and that's a very important element of what we need to do in centralized air conditioning system. And in the finally, we need to also look at the end of life management. So what do we do with the end of life for the refrigerants? So let me start with each of these steps and talk a little bit about that in the presentation. So the first step is how do we reduce the capacity of centralized air conditioning system? Now these are the 3 pillars that earlier webinar on this webinar series focused on in terms of the energy efficiency of systems in buildings. And so the very good important element is an envelope design. So you need to reduce the heating and cooling gains inside the buildings through a good envelope design. That includes a good wall, roof, window design that's suitable for the climate. You can't use one size fits all. You have to select the right design for the right climate. You have to minimize the envelope leakage. So once you have a good envelope system design, then you can think about how can we use passive strategies. And so by envelope design, what you are doing is actually reducing the capacity of the system and the need of refrigerant. The quantity of refrigerant goes down because the capacity of system is going down. Then you think about a passive strategies in terms of how we can use thermal mass of building, when can we use free cooling when it's available outside, and what can be done in the design with occupants, such as the personalized cooling systems, design where we give control to the occupants of their comfort, the opportunity to adjust the window openings. This strategies again allows us to reduce the capacity of air conditioning system. So that's the second step of actually trying to reduce the capacity of CAC system. And finally, there will be in extreme climate conditions where you will need a centralized air conditioning system. And in these conditions, we'll actually have to first think about how can we use a non-refrigerant based low energy cooling system in the building. So you can use an example in evaporative cooling in the buildings. You can think about a variable speed components, very personalized systems, saying, how can we have systems which provide comfort specifically to the occupants. And it is also becoming quite useful to think about hybrid systems where we have 2-3 technologies that are integrated into the air conditioning systems, and then you use the technology which is most suitable for that kind of that type of period of the day, period of the year. And so hybrid cooling system is another way we can reduce, because now you don't have to size your system for the entire cooling need of the building, but you can cut it down in small pieces and use the certain components. So once you do that, once you select that, the sizing of the reduce the capacity of systems, the next step would be is we need to go into thinking about what kind of refrigerants we use. And I am in here just showing one slide. I've cut down several slides because the expert speakers after me are going to talk more about what are the limitations of current refrigerants and how we need to move to the next generation of refrigerants and what are those refrigerants. But in essence, we want to use the refrigerants which are more climate friendly. They have lesser adverse climate impacts. And this is one slide again on the protocol Kigali amendment, where this is talking about a hydrocarbons phase down timeline. So it talks about a different years in which the certain countries and certain species are places are phasing down the use of hydrofluorocarbons. Again, this will be discussed more in detail by Professor Devota in terms of the future of refrigerants. So now let me shift here in terms of how can we increase the refrigeration efficiency. So what are the approaches that one can do to reduce the refrigerant volume in refrigeration system? So once after doing all of these, you have decided this is the capacity of the system that I need in my space. I need to first think about how can I reduce the refrigerant volume. So you can think about optimizing the length, location of the component. How can the diameter of the the refrigerant components can be reduced? You need to think about reconsidering and re-optimizing the design, saying how the alternate design can lead to a higher system efficiency. How can we use a higher efficient components such as compressors, oil-free compressors and a variable speed compressors can lead to a significant reduction in the refrigerants in the refrigeration systems. You can think about also having secondary loops. You can use water or brine as the secondary loop, so you can actually cut down on the length of pipes of the refrigeration systems. The third approach one can think about is how can we improve the heat exchange within the refrigeration system. So you can think about efficient heat exchangers which are more advanced, such as a microchannel heat exchanger, or changes in design. Instead of symmetric design, you may think about asymmetric channel design, where you can actually try to minimize and increase the efficiency of the heat exchange within the refrigeration system. And finally, the controls. You can think about how can you have a better algorithms. You can use instead of thermostatic expansion valves, electronic expansion valves, and a variable speed component. So these are the ways we can actually reduce the refrigerant volume in refrigeration systems and increase the refrigeration efficiency. Now, if we talk about the refrigerant life cycle in centralized air conditioning system, which is very similar to other use of refrigerant as well, it contains of 6 steps. A production at a facility, in a manufacturing facility, then the CAC system gets installed on site. And then throughout the operation, it needs to be managed, how the refrigerant is being used and how we are optimizing the system operation in at site. The fourth step is maintenance, is how do we maintain and ensure that there are no leaks, and how it's detected and how it's then sealed, and during even the maintenance, how we recover and store the refrigerant so it doesn't, the gases, we don't lose those gas leading to a adverse climate impact. And then recovery and recycling are another 2 elements which are very, very important to ensure that we can minimize the climate impact of refrigerants. So I'll go through a simple but a plan which has worked quite effectively in various buildings. So to reduce the leak rate in centralized air conditioning system is through a good maintenance system and a good approach of leak detection. So again, you want to have a systematic leak detection. So you need to have a systematic strategy of how you can do a leak detection. There needs to be a quick repair. So, you know, and often we end up seeing the cases where the leaks are being left undetected for a long time. So you need to immediately repair to minimize the loss of refrigerant. You need to use the right tools for repair so that it does not happen again and again, and then have a strategy of how we can prevent the leakage next time. So and to do that, you can come up with the goals. For example, there are no leak goals, or there are certain percentage of leaks goals. So some of the key performance indicators that often are used are, you know, leak rate. So percentage of refrigerant leaked in a year compared to the total refrigerants installed in a facility. The identification, how quickly that was identified or how it was identified, the leak. The repair time, how quickly it was repaired, and the response time. So these are the metrics indicators that you can have in your maintenance system to reduce the leakage rate. And finally, you do a performance monitoring to verify that the systems that you have, the strategies that you have, is actually working for the site. Now, talking a little bit about, very briefly, about recovery and destruction of refrigerant. So you actually, while there will be times when you have to maintain the system and you will actually have to pump down the refrigerant. So you pump down the refrigerant to recovery equipment and you try to conduct the repair and recharge the unit. So if the system is repairable, then you actually try to recharge the unit and reuse the refrigerant. But if the equipment is faulty, then you put it in a recovery unit and you either do recycling, or if you cannot, if the machine is not functioning, if, you know, machine has reached its end of its life, then you actually take it to the destruction plant, and you have to have a system in place, you know, where you decompose it in the substance that do not harm the environment. So this recovery and destruction of refrigerant is very important to minimize the climate impact of refrigerant. And in the brief talk, I want to just end with this last slide showing that, you know, while I've talked about different elements, you know, reducing capacity, efficiency, maintenance, and how it can be handled at the end of life, and a climate-friendly refrigerant selection, all of them have to work in sync to actually minimize the climate impact of refrigerant, keeping in mind that that's the most important solution that we have that can have the highest effect on not reversing, but at least minimizing the climate impact. So all of them have to work in sync to actually to conduct a good refrigerant management in a centralized air conditioning system. With that, I will complete my presentation and I will go to the next part of the presentation where I'll introduce the next speaker. So next speaker that I'm going to invite is Professor Omar Abdelaziz from the University of American University in Cairo. Dr. Abdelaziz is an assistant professor of thermofluids with more than 15 years of R&D and project management experience in energy efficient building technologies, sustainable energy production and utilization, alternative cooling and heating technologies, and alternative global warming refrigerant. He led the building equipment research group and was responsible for a diverse research program with an annual budget of $18 million US dollars. In September 2017, Dr. Abdelaziz moved to Dubai, UAE, and established a Cleat Consulting, where he catered state-of-the-art consulting and R&D services for green buildings globally. He actively collaborates with leading appliance and equipment manufacturers on the development of advanced and state-of-the-art HVAC and R equipment. Dr. Abdelaziz is currently a member of the United Nations Ozone Secretariat Techno-Economic Assessment Panel, PEEP, and a co-chair of its Refrigeration, Air Conditioning, and Heat Pump Technical Options Committee. He has published more than 100 peer-reviewed papers and holds several patents. With this, I invite Dr. Abdelaziz to take over for the expert session too.
Thanks, Dr. Shukla. It's a great pleasure to be here, and you've done a great job in introducing this this session. I'll try to be as brief as possible and provide a quick insight on alternative refrigerants for centralized air conditioning systems. So in general, the history of refrigerants, where it starts and where it is evolving right now, it started in the 1800s, working on what we said back then, the first generation of refrigerants, and whatever worked was used. So at that time, efficiency was not important, safety was not important, and also we had poor cost. At that time, people worked with ammonia, carbon dioxide, hydrocarbons, water vapor, even sulfur dioxide and methyl chloride. So we see some of these are notorious, some of them are still used to date. And then we moved to the era of what is safe, what is cost effective. So this enabled the innovation and moved the technology much faster. So this is the era of Carrier and Midley. This is what we call the second generation, where safety and stability became important. Ammonia was able to remain a viable refrigerant, especially for industrial application, but CFCs like R11 and R12 became the staple for air conditioning application. And then HCFCs also emerged like R22 and R502. Then the Montreal Protocol emerged, and we found that CFCs and HCFCs are harmful for the ozone layer, and we wanted to preserve our ozone. So the ozone protection era moved us to the third generation of refrigerants. That was between 1990s and 2010. Again, ammonia was able to continue as an industrial refrigerant of choice, for industrial application and some commercial application. And HCFCs were used as transitional refrigerants, including R22 and R123. And then we saw a burst in the use of hydrofluorocarbons like R134A for refrigeration, air conditioning, and automotive application, R410A for air conditioning application, R404A, as well as other blends. Now, people understood that global warming is going to be an issue. So starting in 2010, there were some discussion about the global warming, how can we avoid global warming? And there was a limited optimal choices. How can we compromise between safety and design challenges and energy efficiency? Looking at the direct emission and the indirect emissions. And that is why we started to look at total equivalent warming impact, or TEWI, or life cycle climate performance, or LCCP. Again, ammonia continued to be a refrigerant of choice for many applications, and some low global warming potential refrigerants emerged, whether they are HFCs or hydrofluorocarbons like R32, or hydrofluoroolefins and hydrochlorofluoroolefins like 1234YF, 1234ZE, and 1233ZD. Also blending these with some other HFCs, even with higher GWP, was an option to try to play with the flammability and increase the efficiency, and to be able to match the baseline refrigerant. So we heard a lot about alternative refrigerant blends. And there was a renewed interest in natural refrigerants, including carbon dioxide and hydrocarbons. Of course, carbon dioxide is better in transcritical application where the ambient temperature is not that high, and hydrocarbons are always favored when you have low refrigerant charge. On this chart, we just simply summarize the difference between the global warming potential for different refrigerants. So we can see here on the left-hand side, these are the natural refrigerants. So you can see carbon dioxide as 1. So this is a log scale. And with a log scale, you can see that 1, this is 10, 100, 1,000, and 10,000. So the natural refrigerants are all below 10. the first generation of fluorinated refrigerant like R12 and R11 were quite high, like more than 10,000 for R12. I capped it here at 10,000, but actually more than 10,000. For R11, it's quite high, close to 7,000 or so. And then for Hcfc, like R22 and R123, you can see R22 is close to 2,000 and 123 is close to 100. For Hcfcs, they are all higher than 1,000, and the highest of them is R404A, close to 4,000. Then we have what we call the low GWP refrigerant, and we're starting with R32 at about 700, and all of the others are close to 1 except for R123 MZZ, that is about 3. All right, so what is required? What is the properties that we want to look at when we look for a refrigerant gas that meets our current challenges? So the first thing, for air conditioning application, we want the boiling point, which is the normal boiling point, where would the refrigerant boil at ambient pressure, to be between minus 40 degrees F and 32 degrees F, or between minus 40 and 0 degrees C. We hope to be able to get it as non-flammable, because if it's non-flammable, then we don't need to worry about refrigerant or system redesign. But can we do it? That's a big question. It should be less toxic, or preferably non-toxic. It should have chemical stability inside the machine. So when we put the refrigerant inside a sealed system, we don't want it to disintegrate. We want it to be stable over the lifetime of the equipment. However, if it is released to the atmosphere, it should break down to harmless products if released, and that is important in order to reduce its atmospheric lifetime, and as such, reduce the global warming potential. If it has pungent odor, that would be great, because then we would have human leak detection, because when it's released into a room, I can detect that there is a refrigerant leak, and I can act accordingly, like open a window, open the door, flush the indoor, and so on. It would be great if it's inexpensive, and it should not contain chlorine, bromine, or iodine, because these are all ozone depleting substances and must have short atmospheric lifetime to minimize GWP. That is how the fourth generation refrigerant were created. They react with common atmospheric species to shorten the lifespan. There is a couple of chemistry approach. The first one is to increase the number of hydrogens, but that increases flammability, include oxygen or others, reduce chemical stability by adding bromine or iodine, but again, that is quite questionable because it impacts the ozone depletion, or use unsaturation, like adding double or triple bonds using olefin designs. The best approach between these is to use the unsaturation and hydrogen, and that is how we move towards hydrofluoroolefins, hydrochlorofluoroolefins, and hydrocarbon refrigerants. The issue is the flammability increases. So the issue is not natural fluids versus synthetic fluid. The issue is more the environmental stewardship and delivering cool or heating with the smallest possible life cycle climate impact. We don't need to worry whether it's a natural refrigerant or a synthetic refrigerant. We just want to make sure that we are not impacting our environment. So how can we do it? It's a trade-off. There is what we call environmental performance. We want it zero ODP or as close to zero as possible with low GWP, or we call it reduced GWP. It has to be safe to the consumer, energy efficient. That is important to reduce the indirect CO2, because this is the amount of emissions that is happening along the life of the equipment. We need to understand the intellectual property consideration. Is it easy to use in developing countries or not? Do we have to redesign the equipment, or can we use it as a drop-in refrigerant? Because that affects the transition cost. And finally, what is the product sustainability? Can we use this product or this technology over a long time, or maybe in 5 years, this technology is not gonna be available, right? So we want to make sure that it is sustainable, that there is enough supply, there is enough material worldwide to support the use of this refrigerant over a long term. Safety is usually defined according to the ASHI standard 34 or ISO standard 817. And like a quick summary of how these are is this table here. Basically, we define the flammability, the toxicity, and the flammability. So if it is safe and non-toxic, we call it class A. And the borderline between class A and class B is the occupational exposure limit. How much, what is the allowable exposure limit? So if we can release more than 400 ppm in the room, and we still think that the refrigerant is not gonna cause a toxic environment, then it is a class A. And if less than 400 ppm or less is going to cause a toxic environment, then we call it class B. Examples of class A include, most of the HFCs like R134A, even CO2, let's see, Hfos, and all these refrigerants. Examples of class B include ammonia, for example. So ammonia at less than 400 ppm becomes a toxic environment. In terms of flammability, so we start with 1 and move up. So 1, there is no flame propagation. That doesn't mean that it is not flammable. The refrigerant can be flammable, but it will not propagate the flame. So it is safe. So we start with 1 and move all the way to 3. A new limit was created recently, which was called 2L, which is a case where the refrigerant will not sustain fast flame propagation. So we call it feeble, slow flame, and slow, low pressure rise. And then we have A2, where the refrigerant burns faster and there is low heat of combustion, and A3, that or 3, that is when it burns at explosive speed and there is high heat of combustion. Again, examples for A1 include like normal refrigerants like R134A, R22, A2L, some of the Hfos like R1234YF. A2 includes, for example, R152A. A3 are mainly hydrocarbons like isobutane, propane, and so on. All right, so how do we select the refrigerant? It depends mainly on the compressor technology. Is it a centrifugal compressor, a screw compressor, or a scroll or reciprocating compressor, or even a rotary compressor? So when we talk about central air conditioning application, like if it's a centrifugal or large air conditioning machines, like greater than 1,000 ton, then we use what we call low and medium pressure. So low pressure and medium pressure. Examples include, as a baseline, R123 and R134A for medium. And then for screw compressors, this is medium and some high pressure application. Typical refrigerant are R134A and in the past R22. This is between 500 and 5,000 tons of refrigeration. For smaller capacities, we call it high pressure, mostly in the past R22, now with R410A and R407C. And you can see here, this is a figure that is captured from Train API refrigerant brochure. For low pressure, we don't have too many options. So there is the Hfo R1233ZD, and you can see like the pressures are quite low. If you look at in TSIG, like in the evaporating pressure is subatmospheric, and you can see that that offline R123 is subatmospheric, 1233ZD is again a little bit above atmospheric, and condensing pressure is always above atmospheric. And you can see for medium pressures, you are at much higher pressures. High pressure, it's almost double that of the medium pressure. So for R123 alternatives, we can see that there are some non-flammable refrigerant with GWP ranging between 400 and 600. This is a higher GWP than R123, so it's not necessarily a good options. There are some flammable options with GWP less than 150. Most of the alternatives are with good efficiency, and there are some near design compatible alternatives. However, the glide might vary quite a bit. So if you look at the capacity over that of the R123 and the COP versus the COP of the R123, of course, at 0 and 0, so that means that you are at 123. In this corner, you have lower COP, lower capacity. Here you have lower COP, higher capacity. Here you have higher COP, higher capacity, higher COP, slightly lower capacity. So you can see that like R514, you have slight reduction in COP, slight reduction in capacity, and this can be corrected using some engineering application. For 1233ZD, you have significantly higher capacity and slightly lower COP, like 1% lower COP. And again, this can be corrected using proper engineering. Of course, 1233 is of a very low GWP. So this is going to be a good option if we can match the same efficiency. For medium temperature application, again, there are several low GWP available today, including 1233ZD, 1224, YD, 514, and 1234ZE. These are when we target commercial air conditioning application. Of course, for automotive air conditioning, the choice was simple, 1234YF. Most of these are non-flammable, good efficiency, and no glide. For smaller applications like R14A, we have lots of options. Some of them, or actually most of them, are flammable, except for the newly developed R466A. We can see here the environmental impact. So the refrigerant efficiency, which is the COP, and you can see that for low pressure application, when we moved from R11 to R123, we had a reduction in efficiency, and then with R245 FA, even lower efficiency. But for the alternatives right now, like 1233ZD and 514, we can almost match that of R123. For medium pressure, again, you can see for like if we compare with this baseline, the ZE almost matches the COP, the same COP of the baseline. However, it is has a burning velocity of 0, but it is 2L, and you can see that 513A has slightly lower COP. It can be matched using some engineering, and it is non-flammable. For high pressure application, again, you can see that most of the alternatives have higher efficiency than the baseline. If I have time, I can just show very quickly that experimental analysis on packaged air conditioning applications, both for R22 and R14A, you can see like this is the R22 unit, this is the R14A unit, and the R22 is roughly 27.2 kilowatt. This is a little larger, like 11 tons. So this is 7.5 and this is 11 ton. And you can see here the performance of R22, again, at 100% capacity of the R22. So this would be R22. You can see that at 35-degree ambient conditions, the only one that has higher COP is Arkema 20A. Although, and on the other hand, higher capacity is with R454A and Arkema 20B. In terms of when you go to higher temperatures, like 52 degrees ambient temperature, again, you can see you can have higher efficiency and higher capacity on this end. Again, proper engineering, you can match that of the baseline refrigerant, because the difference between the baseline and the alternative refrigerant is not that big, especially with R44B. We are talking about 5% lower COP and slightly higher capacity. So this can be matched. Again, Arkema, you can also match it. You have lower capacity and slightly higher COP. For R410A application, we can see that most refrigerants have better COP, and some have exactly the same capacity. Some have slightly larger capacity at 35 degrees ambient, and at 52 degrees ambient, all of the refrigerant have better capacity and better COP. With that, I'd like to thank you and thank Dr. Yash for the opportunity.
Thank you, Dr. Abdulaziz. That was very helpful to know about the alternative refrigerants for centralized air conditioning systems. What I would do is I would hold all the questions till the end of the session, and I'll go to the next expert speaker. I will invite in the next session Professor Sukumar Devota for a talk on CAC vis-a-vis Montreal Protocol and climate change challenges for developing countries. Professor Devota has immensely contributed to the field of energy, environment, and green technologies. He has served and continues to serve in many prestigious national and international committees, including Montreal Protocol Ozone Cell, MOE-FCCC since 1992, UNEP Technical Option Committee on Refrigeration, AC and heat pumps. Dr. Devota was awarded the US EPA Stratospheric Ozone Protection Award in 1997. As a member of IPCC, he has also received a citation from IPCC, which was awarded the Nobel Peace Prize in 2007. Professor Devota was awarded Distinguished Alumni Achievement Award by Salford University, UK in 2017, and AC Tech Distinguished Alumni Award in 2021. Dr. Devota was listed in the Stanford University top 2% world's most cited scientists in environmental science and engineering. Professor Devota has guided 25 research students for PhD and ME, MTech in chemical and mechanical and environmental engineering. He has co-authored many books and chapters in books and also published more than 220 research papers in international journals. With that, I welcome Professor Devota for the next session. Professor Devota.
Okay, so thank you, Yash, for the introduction, and I'll just share my slide. Can you see that?
Yes, not in full screen mode yet, sir.
Yeah, that's right. Yeah.
Perfect. Thank you.
Okay. So thank you, Yash, for your nice introduction, and thank you, Omar, for covering some of the preliminary things which I wanted to cover, and therefore my job is easier. And I'm going to speak mostly on refrigerant choices with respect to how do you deal with Montreal Protocol and climate change, and what are the issues for developing countries. So just in case people don't understand the refrigerants, because it's too easy to say HCFC, HFC, but then you have to understand that each has its nomenclature. So when we have a chlorine and fluorine and carbon, then we call it CFC. Likewise, CFC12, which was used in the refrigerator, CFC11, which was used in large centrifugal chillers, HCFC22 used in air conditioners, R22, then R134A, HFC134A, which is used now in mobile air conditioners and in some refrigerators, Hcfo 1234YF. Why do we call Hfo? Because it's hydrofluoroolefin. So you will see that it has a double bond. So it is an unsaturated compound, so we call it olefin. So that's why you get O there, HFO. Then we have hydrocarbons like 290 is propane. It is just contains hydrogen and carbon and hydrogen. So you have C3, you have a C39, C38, which is HC290 or propane. And when we talk now about refrigerants, we have to deal with two major parameters, issues, that is ozone layer depletion and global warming. So when you say ozone layer depletion, as was mentioned by Omar, we have almost phased out ozone depleting refrigerants, but still there are like R22, R123, they are all ozone depleting refrigerants. So we are yet to completely phase them out. Then we have a global warming issue. That means it is characterized by GWP. So if you want to take both into consideration, we need to worry about refrigerant emissions throughout its life cycle, energy efficiency, because energy efficiency is responsible for CO2 release in power from power stations. So the more the energy you put in, the more CO2 you release. So energy efficiency becomes an important issue. Recovery and recycling. Already Yash had said, how do you manage refrigerants by recovering and recycling? So just to give an idea, the ODP is a kind of a relative term. It's not an absolute value. It is only determined with respect to another refrigerant. So we call it ODP. Means it is ODP of CFC 11 is kept as a standard ODP of 1. So any value you are quoting for other refrigerant, it's with respect to R11. Likewise, global warming potential for halocarbons, we used to quote halocarbon global warming potential. That was again with respect to R11, but now globally we define global warming potential with respect to carbon dioxide. So carbon dioxide global warming potential is 1. So I have given you some values of now R12 is 8,100, 134A is 1,300, 600A is 4. So we talk about GWP. There are many refrigerants even today, what we are using, they have a fairly high GWP. And these values are taken from IPCC assessment report 4, although these values are being revised later, but for political purposes as well as policy purposes, we still use assessment report 4 values. And some people keep on asking, what is low GWP, what is high GWP? So in UNEP, our talk, we tried to address this question. We came up with some numbers and classification. Although this is not officially accepted by anybody, but this is the proposal we made. And you can see that when we say low, we mean something like less than 300. When you say medium, it is 300 to 1,000, and high, above 1,000. So most of the current HFCs will fall under high, except for R32. And then say R32 GWP is 675, so it will fall under medium. HFC 152A is low because it's about 100 plus, and 123 is low. But most of the HFOs and natural refrigerants, we call ammonia or hydrocarbon or CO2, they'll all fall under ultra low or negligible, and less than 10, it's very difficult to determine GWP so well, because it is done, all GWP values again is done by theoretical simulation. It is not measured value. So when you do simulation for low GWP, it becomes very erratic, and it has to be taken with a pinch of salt in terms of its reliability. But still, most of the HFOs will have low GWP. And most of the CFCs, you can see from here, they are all very high, above 3,000. And HFC 23 is the ultra high, but that is not used in a major way in air conditioning and refrigeration, except as a blend. but it comes out as a product, co-product when you make 22. So 23 is not, it was used once upon a time, but now it is not used. So we'll be talking mostly about these refrigerants, including HFOs. And I just wanted to, I just wanted to go back to this, the debate started when EU put F-gas limit as 150. They wanted to limit refrigerants higher than 130, higher than 150, not acceptable for mobile air conditioner. But now they are limiting in many applications refrigerants to be 150, and some of the countries have started imposing carbon tax depending on the GWP. So high GWP means you pay more, and not only pay more for the price, but also tax. Yeah, so in most of the developing countries, we still use HCFCs because the HCFC can be used up to 2030. For instance, country like India, we are still using HCFC 22, R22 in the air conditioners, but the new R22 is not sold. It has been banned, and most of them will use R410A, R32, 290. But still they are used in service, and soon by 2030 you have to stop using 2030 R22 or 123. So this is the phased on. We have gone through this, and only a small portion is allowed for tail. But I can tell you, market is moving faster than this regulatory steps. That's where the protocol, this environment gets saved. Although the Montreal Protocol gives you a lot of leverage, but global trend is faster than this, and therefore most of the countries, in order to be in the market, they phase out all old refrigerants and start introducing new refrigerants. Now, when we are doing, developing countries are handling HCFC phase down. I want to just differentiate between HFC phase down and HCFC phase out. CFCs and HCFCs were phased out, meaning by 2040, all HCFC consumption should become zero. Like if you see my previous slide, it should become zero. Whereas in the HFC phase down, it doesn't become zero. You have to only phase down to something like 10% at the end of the target year. So this is coming under Kigali. In between we had Kyoto, but Kyoto is almost infructuous, and now Kigali has been taken in under Montreal Protocol, and you can see there are 4 groups. EU started its own HFC phased on very, very early in 2015, and the blue, all these blue are for EU. So they can use quite a bit. They have a very long usage up to 2047, but they started very early. Whereas non-Article 5 countries, that is, which means all developing countries like Europe and US and Germany and France, they have from green, the bars you have to see is green, and you can see that they move faster, and then they come down, very, very fast towards the end. So this is the second group, but this is not under Montreal Protocol. For EU F-gas regulation was independent of Montreal Protocol, and they are still following because it is conforming to developed country status. And you have two classes of developing countries, Article 5 countries. The first class is the yellow, and they start like this and end up here, 2047. But they start phase down much earlier, 2024. Whereas the second class of people, countries, including India, they start only at 2028 and they go down. They have to do it fast because this is the biggest challenge. All others come down slowly and gradually. You can see that. Whereas country following this group 2, they not only start late, but they go slow and then crash here. My personal view is that this is not going to happen. All of them will go like this. Now, that's the way the market is already, for instance, you can go to any developing country in Asia, you will find that R410A is already there, R32 is there, R290 is there. So they have started phasing out HCFCs, and they have also started phasing down HFCs because they have started using lower GWP and hydrocarbons, ammonia. So market force will make changes different from what is regulatory systems demand. This is an interesting graph I wanted to share, published by our colleagues from UNAP ORTOC group. And what they did, what's going to happen to different growths of different groups and how they have to deal with average GWP. And they ultimately they showed that whatever you do towards end or sooner, another 20 years time, you have to start using something like less than 150 GWP. And some countries will have to use less than 400. And some countries will have to use less than 150 or even. So that means most of the refrigerants we are dealing with today will go away another 15, 20 years time. So this will eliminate all HFCs, including 32. It will only mean Hfos, hydrocarbons, ammonia, CO2, and probably water. And this is going to be a big challenge for developing countries. So if you go to textbooks, you'll read, even today's textbook, you'll read that thermodynamic evaluation and COP, all those things. Right? Although you need to do, but you can get a fluid which is thermodynamically very attractive, but if it doesn't satisfy environmental characteristics, that fluid is not going to be used. So that is the basic difference between what was taught 20, 30 years ago and what will happen today. No fluid with any non-zero ODP value, it's completely gone. Low GWP. Here I put low GWP. Sooner it will become ultra low GWP, another 20 years time. Then you can't use any fluid which has a residual ODP or low GWP. But earlier, old traditional books used to teach about flammability and said, oh, you cannot use flammable refrigerants, you cannot use toxic refrigerants except ammonia and VOC and all that. Now it's all gone. You can use any of these things with improved technologies, particularly with respect to improved stringent standards, stringent manufacturing practices, and almost zero leak technologies. And cost is not an issue today because most of the new refrigerants will be more expensive to start with. You know, if you want to buy any new refrigerant, you pay 10 times the old refrigerants or more, much more. Yeah. So, but what has not changed is performance. You will not use any of the refrigerant if it is going to have performance lower than the existing one. That compromise is not made. So you have a real challenge in the technical challenge that you have to choose a fluid which is low GWP and affordable cost, but it has to still perform. Like Omar said, most of the new refrigerants are better than of course, you can make a refrigerant as best as possible through design changes, but then cost is a factor. Okay. One of the reports of TEEP said that it doesn't matter what refrigerant you use, you can match the existing system through various technological options, which is true. You know, what was spent on R&D for energy improvement in 30-40 years ago was negligible. Today, all the effort is going towards safety and efficiency. So, you know, these are the fluids which we used and we have phased out. All these things are ozone depleting substances. These are the fluids we are now, some of the fluids we are using, R123 and R122A, R22, R134A, they'll all go, and then you will end up only with towards margin. This is a plot of ODP versus GWP. So you will have to go to the origin, and the origin will have only natural refrigerants and HFOs. Today in the HVACR market, you have mixed all kinds of refrigerants because, as I told you, 22 is still used, but will get soon phased out completely. In new equipment, 22 is gone. Nobody will make new equipment, but it's still in use in some of the old equipment. And 123 in centrifugal is still there, but there are new refrigerants which have come in. And then you have 32, 134A, 1234 YF, ZE, 336, and ZZ. Then we have Hcfo. This is a little bit of controversy because it is still hydrochlorofluoroolefin. That means its ozone depletion potential is not zero, but it's close to residual zero. So it is still used now and it is being debated. Then you have blends, which are 4 series, 400 series. Then we have blends of 500 series. 500 series means they're azeotropes and they have no temperature glide. 400 series means they have a temperature glide. So you need to take care of the refrigerant heat exchanger design when you deal with 400 series, like 407C, 410A. 410A has a very low temperature glide compared to 407C. So 407C is close to 4 and 410A is very marginal. So it almost behaves like a single component refrigerant. And the issue is, while we are struggling to change the refrigerants, the growth is going to be phenomenal. So the refrigerant growth will be there. Therefore, the industry is struggling to find out how to maintain growth, but at the same time, do not increase global warming potential gases. And you can see that market shares of refrigerants and growth in this slide. And Omar briefly mentioned about life cycle climate performance. This is a tool which we have been using in the past, but not many people took it seriously, because it started with TB, total equivalent warming impact, and then it was broadened and refined to call life cycle climate performance of refrigerants systems. This is LCCP encompasses entire life cycle, production of the refrigerant, transportation of the refrigerant, and charging, installation, running, operation, then end of life. Therefore, it encompasses the entire life cycle of the unit, and you can calculate and compare the performance of a refrigerant in a system using LCCP analysis. But you have to bear in mind, energy is more important. Energy efficiency. Energy means, when I say energy efficiency is more important in the entire system than anything else. That dominates. That's why I said, I reiterate that in any refrigerant you choose, there will be no compromise on the energy efficiency of the future systems. In the world, particularly Europe, it's going in a big way using ammonia. That is because ammonia is a very efficient refrigerant. But as Omar said, it's a B2L. That means it's not only low flammability, but also toxic. So it's one of the few refrigerants which are classified as toxic. 123 is B, R123, and then ammonia is another. Very few refrigerants, almost you can number with your finger, one hand, B class. Most of the refrigerants are A class, non-toxic. But ammonia is a B2L. It has ultra low GWP because close to zero. Today, because it's toxic and flammable, the technology has improved significantly to reduce the charge. Entire design is such a way that you don't connect interconnecting pipes too much. They are as close as possible between the reservoir and the compressor reservoir and feed reservoir and heat exchanger. So they made the interconnecting pipes as short as possible, then used plate heat exchangers to reduce the residing refrigerant in a system, and therefore you can get very low charge, 1.3 kilogram of ammonia per kilo water. But then now you get ultra low charge, 0.06 kilograms. So that means they have reduced the charge by order of magnitude and still maintained energy efficiency better than the old ones. And the standards have been revised. And therefore, in Europe, particularly for heat pump applications for space heating, ammonia has been used in public buildings, and not just industrial refrigeration, but even in public buildings. And I've given loads of examples, including airports, London Airport, Oslo Airport. I happened to be on the day of Oslo Airport inauguration with ammonia. All our RTAP members were taken for a visit, and we visited one of the largest ammonia heat pumps in the world. That time was being inaugurated for heating, providing space heating in Oslo Airport. So since then, that was a long time ago, about 30 years, 25 years ago. Now these things have changed. Now there are many more ammonia chillers with ultra low, and therefore it's going to be interesting to watch whether the problem in developing country is the ammonia is still unsafe because they don't follow most of the safety regulations, and they bypass some of the international standards because they're too expensive to implement. When you compare with halocarbon refrigerant or one, like any other refrigerant, HFC, you will find that cost of ammonia is much more if you follow all these international standards, because they have to follow the standards. And these things happen, and therefore ammonia is still going to be an issue. The last slide I have is absorption chillers and poly generation. Absorption does not use any refrigerant per se, but then we call it, it uses either water or ammonia as the refrigerant. But if you take lithium bromide water, it uses water as the refrigerant, and it has similar to mechanical vapor compression, but then you are dealing with pump rather than compressor. Therefore, electricity requirement is very, very marginal compared to mechanical vapor compression, and it uses heat rather than electricity. So you can't really compare COP of absorption with COP of mechanical vapor compression systems. And now you can buy double stage absorption chillers with 1.2 COP or triple stage with 1.8. And these are all commercially available, and they use water and lithium bromide. The advantage of that is it works on heat rather than power, and therefore you can use waste heat to run a absorption chiller, and the waste heat can come from even a gas engine or a generator, diesel generator. So by cooling from the exhaust of the gas engine, you can recover heat and run a chiller to produce cooling. Then the jacket can be cooled to produce hot water. The engine will produce electricity. So we call it tri-generation. It produces electricity, cooling, and heating. And there are multiple possibilities possible. And this is now becoming very popular. And there are two major manufacturers, one in China, Broad, another in India, Thermax. They sell bespoke. And please remember, absorption chillers are not packaged to the extent like mechanical vapor compression chillers. They're all bespoke because you have to decide whether it is going to be from the exhaust gas or hot water driven or steam driven, high pressure steam driven. Accordingly, they have to design, but you can buy them up to one chiller. You can buy up to 1,400 tons of chillers. It's huge ones. I've given one example here where they have recovered heat from gas engine, 1.1 megawatt gas engine. It takes heat from exhaust to get hot water and run it, chiller, and then this gas engine jacket is cooled, hot water. Because in a gas engine, about 30% goes to electricity, about 30% goes to exhaust, 30% goes to jacket. So 100%, if you take, it will be about 100%. Approximately one third will go. So you can get 1/3 of the heat utilized to produce almost equivalent of cooling in kilowatt. So it has a lot of benefits. So I'll stop here. Thank you very much. So
Thank you, Professor Ryota. That was a very, very interesting presentation. And we will again hold the questions for now, and then I will take the question towards the end. With this, I'll move to the next session. The next session is from our expert at RES4, introducing Technical Assistance Program 6730, promoting life cycle management of fluorocarbons. This presentation is given by Mr. Shintaro Fuji, who is Environment and Climate Change Specialist in Sustainable Development and Climate Change Department of Asian Development Bank. So let me introduce Mr. Shintaro. So Mr. Shintaro Fuji manages the Japan Fund for the Joint Crediting Mechanism, JFJCM, which promotes advanced low carbon technologies. He also supports the operation on climate change and environmental issues. And prior to joining Asian Development Bank, he worked for the Ministry of the Environment of Japan for more than 15 years. With this, I will stop sharing my screen and I will hand it over to Mr. Shintaro Fuji for his presentation.
Yeah, thank you, Yash. Let me share my screen. Okay. Can you see my screen?
Yes.
Okay.
Yes, it's perfect. Thank
you. Yeah, thank you. Yeah, so good morning, good afternoon, good evening, everyone. So I'm Shintaro Fuji from Climate Change and Disaster Risk Management Division, ADB. So I'm very pleased to have this seminar in cooperation with Jim Miao's team. I would like to introduce our TA, promoting life cycle management of fluorocarbons. As other experts mentioned, the fluorocarbons have huge global warming potential, and thereby the fluorocarbons management is key to mitigate climate change. Jim Miao's TA and our TA are relevant, and we aim to realize synergies through implementation of both TAs. Okay, so our TA is one activity of ADB's carbon market program. So prior to explaining our TA in detail, let me give a brief background on the carbon market program. ADB has built a strong institutional history of being involved in carbon markets. ADB launched the flagship carbon market program, CMP, in 2005 to provide innovative carbon market support to stimulate greenhouse gas mitigation activities in developing member countries of ADB through the technical support facility, the Future Carbon Fund, and other activities. The CMP was designed to address key financial barriers to development of emission reduction projects by providing upfront carbon finance while simultaneously building essential carbon market technical capacity. CMP's support has expanded to respond to changes in the international climate change regime to include assistance with domestic carbon pricing and emissions trading schemes, bilateral crediting mechanisms, with the establishment of the Japan Fund for the Joint Crediting Mechanism, which I'm managing. This was established in 2014. And market-based approaches under Article 6 of the Paris Agreement. During COP24 in 2018, ADB launched the Carbon Market Program 2.0 to support developing member countries to access carbon finance through domestic and/or international carbon markets to incentivize mitigation actions aligned with their nationally determined contributions under the Paris Agreement. And to continue ADB's leadership role in driving sustainable development outcomes through carbon markets. Building on the expertise gained from the first 13 years of CMP, CMP 2.0 enhances ongoing programs and implements new programs such as Article 6 support facility launched at COP24. And recently, we launched the new TA on promoting life cycle management of fluorocarbons, which is the main topic of my presentation today. And this is as a part of the technical support facility. This shows issues that our TA will address. It is estimated that 3.6 billion cooling appliances are in use globally, and that up to 14 billion cooling appliances would be required by 2050. So the growing demand for cooling equipment will increase global warming effects because of the emissions from fluorocarbons, including HFCs and other old refrigerants used in such equipment, and from CO2 emissions, where the appliances rely on electricity from fossil fuel-based energy sources. Hydrochlorofluorocarbons, HCFCs, and chlorofluorocarbons, CFCs, are commonly used as fluorocarbons refrigerants in cooling equipment and in aerosols, and very potent greenhouse gases. HCFCs and CFCs are ozone depleting substances that are very harmful to the environment. So recognizing the impact of HCFCs and CFCs on the ozone layer, countries came together in 1987 to finalize the Montreal Protocol, an international agreement to phase out the production of these substances. As an alternative, HFCs were developed as a new refrigerant, but HFCs are also greenhouse gases with a very high global warming potential value. The use of HFCs has increased rapidly as global demand for air conditioners and refrigerators continues to grow. Global HFC emissions are increasing by 10 to 15% annually and are expected to reach 9 to 19% of projected global CO2 emissions in 2050 in a business as usual scenario. Recognizing this, countries adopted the Kigali Agreement, Kigali Amendment to the Montreal Protocol in 2016, agreeing to gradually reduce the use of HFCs by more than 80% by 2047. While the international commitments are in place, developing countries lack sufficient regulatory and policy frameworks for adopting life cycle management of fluorocarbons and awareness about advanced technologies, innovative solutions, and business models for life cycle management of promote the life cycle management of fluorocarbons and associated energy efficiency improvements in the cooling industry to meet the obligations and the Montreal Protocol and its amendments, as well as the Paris Agreement goals. At the COP25 in 2019, the initiative on fluorocarbons life cycle management was launched by the Ministry of the Environment, Japan. Objective of the initiative is to facilitate concrete actions innovations and collaborations among governments, private sectors, and international organizations to strengthen the life cycle management of fluorocarbons while collaborating on existing activities and frameworks. And ADB is a signatory to the initiative. So we intend to contribute to the objective of the initiative of fluorocarbon life cycle management by supporting participating developing member countries of ADB through this new TA. The life cycle management of fluorocarbons requires various actions from upstream to downstream. So upstream actions include developing, manufacturing, and using climate-friendly refrigerants with zero or low global warming potential, which includes replacing old cooling equipment. And midstream and downstream actions include recovering, recycling, and destroying the discarded fluorocarbons. Through the TA, ADB will closely cooperate with Ministry of the Environment of Japan and other partners in supporting participating developing member countries to promote life cycle management of fluorocarbons. So this shows the overview of our new TA. So this TA just started in May this year, and it will be implemented for 2 years until April 2023. And we have been consulting with 6 potential countries to detail work plan for each country. After the implementation of this TA in middle term, we aim to achieve the following impacts. First, use of zero or low global warming potential refrigerants in the cooling industry will be increased in the participating developing member countries. And the second, use of energy efficient cooling technologies will be increased in the participating DMCs. And for the outcome of our TA, which is more near-term target, we aim to increase DMC's actions to promote the life cycle management of fluorocarbons and associate energy efficiency in the cooling industry. And to achieve this outcome, we will produce 3 outputs with concrete activities. And I will explain more about this in the next few slides. So for the output 1, we will support DMCs to increase their knowledge and awareness of and capacity. And under this output, we will conduct a gap analysis for each participating DMC to provide the current state of and possible areas of intervention for the life cycle management of fluorocarbons and energy efficiency for the cooling industry in the light of global good practice. We will also disseminate the knowledge gained under this TA and enhance awareness on this area through national seminars and regional workshops, as well as some publications. So in terms of output 2, we will identify options for advanced technologies and innovative solutions. First, we will analyze what is available and will identify how to apply those technologies, business models, and innovative solutions in the local context of the country. So last one, output 3. Based on output 1 and 2, we will prepare tailored recommendations on the life cycle management of fluorocarbons to each country. The recommendations will include legal, institutional, and financial aspects. For example, the possible use of a carbon market mechanism under the Paris Agreement, such as the joint crediting mechanism, which is a bilateral carbon market mechanism between Japan and other partner countries. As ADB, so we are also keen to develop investment projects on fluorocarbons from upstream to downstream of the life cycle of the fluorocarbons, including introduction of energy efficient cooling systems in buildings and facilities to destroy the collected fluorocarbons. So this is the final slide. So in summary, ADB is supporting DMCs in promoting the life cycle management of fluorocarbons in cooperation with other bilateral and multilateral partners, and of course, JINMEA's TA team to create more synergies as a signatory to the initiative on fluorocarbons life cycle management. And also, we will particularly review the possible investment opportunities in the life cycle management of fluorocarbons and the energy efficiency improvements in the cooling industry, which possibly use the carbon markets. Yes, so that's all from my presentation. Thank you for your attention.
Thank you, Shantaro, and thank you for the wonderful presentation explaining the scope of new technical assistance program. Since we are running out of time, I would skip the question and answer session. I will note all these questions and I will work with the experts to get the answers to this to the individual questioners and in general to the audience as well. But just to save time, we can move now to the closing session. For the closing session, I would like to invite Mr. Virender Kumar Duggal, who is a principal climate change specialist from Asian Development Bank. Let me read a little bit about him. So Mr. Duggal leads ADB's carbon market program, which provides carbon finance and technical capacity building support to enhance climate action in the Asia and Pacific region. In this role, he manages the Future Carbon Fund, a 115 million trust fund providing carbon finance to enhance competitiveness of the low carbon technologies through the purchase of carbon credits under the Kyoto Protocol. Mr. Duggal is an accomplished professional with a proven track record in the areas of climate change, carbon finance, and international trade cooperation. He has extensive experience of working in multilateral public and private sector institutions in the areas of trust fund management, portfolio management, project development, capacity building, advisory service, technology transfer, and strategic collaborations. So I welcome Mr. Virender Kumar Duggal to give the closing remarks for the session.
Hi, good afternoon, everybody. Thank you very much for a very kind introduction. So distinguished guests, colleagues, ladies and gentlemen, on behalf of the Asian Development Bank, I would like to express my sincere appreciation to all the speakers and more importantly to all the participants for their very valuable contribution to the final webinar of ADB's webinar series on disease resilient and energy efficient centralized air conditioning systems that you all have been part of. So it's my great pleasure to be here and to deliver closing remarks for this month-long webinar series, which to my mind has been path-breaking and very successful. In my closing remarks, let me quickly touch upon the twin challenges of building disease resilient and tackling climate change, because we think both these issues are quite intricately intertwined. As we discussed during the course of this webinar, disease resilient and energy efficient centralized air conditioning systems are need not only of the hour, but also the future times to come, as some of the speakers who spoke before me very nicely articulated. First, they help to reduce the risk of disease transmission. We all know that, and we have deliberated thoroughly about it, that the improper design and operation of central AC systems can increase the risk of airborne transmission of diseases such as COVID-19. And in ADB's DMCs, the developing member countries, the risk of such disease transmission through the air conditioning system are even higher. So this can be attributed to the use of old AC systems, lack of regular maintenance, and most importantly, overcrowding in the closed spaces. The second aspect of the same topic is that the energy efficient centralized AC systems can help tackle climate change also. AC systems, as we know, rely heavily on the HFCs for cooling. However, HFCs are GHGs, the greenhouse gases, with a very high GHG global warming potential as compared to the carbon dioxide. So therefore, it is very important that the proper management of HFCs through the restriction and even prohibition, including the development of its substitutes and the harmless treatment of the critical GHG emissions from the air conditioning systems are taken in the right earnest. So looking at this, ADB recognizes that the disease resilient and energy efficient approach to air conditioning systems can help address the twin challenge of reducing the risk of disease transmission on one hand and on tackling the climate change on the other. So this is very pertinent in the current context as the countries are recovering from the COVID-19 pandemic. As you have heard from my colleagues previously, that recognizing the importance of this topic, and especially for the developing member countries in Asia and the Pacific, ADB is implementing two knowledge and technical support assistance programs. The first TA is on the regional support to build disease resilient and energy efficient centralized air conditioning systems. And this TA aims to promote disease resilient clean energy development in our developing member countries. And this is the TA under which the current webinar series has been held. And the second TA, my colleague Shintaro-san has just introduced. This is about the promoting life cycle management of fluorocarbons, which is part of our ADB's broader carbon market program that I happen to manage. So I'm quite sure that all of you would agree with me that this webinar series has been very timely and very well conducted and very useful for all of these. But to me, the key takeaways have been that the refrigeration management is a great opportunity for all of us to look into and take all the corrective measures. So the key is to collaborate and create synergies in providing the valuable insights to the audience. What we try to do is to work across the teams with managing the two separate technical assistance programs to work together. And our idea is to bring greater value to our member countries and the broader stakeholders. So as you know that ADB has organized these 4 webinars, which focus on the disease resilient energy efficiency in smart operations and refrigerant management. So in that context, I'm very, very delighted to note that the webinar series, which incidentally is part of the TA program, has been very successful. To highlight a few things that I have noted down on my writing pad is that this webinar series has shared key strategies to minimize the risk of airborne transmission through smart and energy efficient air conditioning systems. We have also discussed and deliberated upon the recommendations on how to mitigate the risk of virus transmission and ensure safe working condition in public buildings located in selected countries by deploying efficient, clean, and smart air conditioning systems. So this webinar series, in my mind, has also been very successful in providing an overview of the market-ready technologies that can be implemented in the public buildings located in our region. So overall, I think the webinar series has enabled us to look at the challenges of building disease resilience and tackling climate change under a combined lens and not two separate issues. So I think this has been a great win for all of us, that we have been able to look at the same issues from two different perspectives, and we see that the interests are not mutually exclusive, and there's a significant synergies that can be built upon between the different TAs that we are operating, and we can bring and add value to our developing member countries and the broader stakeholders. So with this, let me thank all the participants for their interest, for their continued participation in this series of webinars, and most importantly to all the resource persons for your participation and active engagement during this webinar series. So I also hope that all of you also took benefits from the knowledge event and have been able to take some good takeaways to bring on the work streams that you are very actively engaged with. So with this, once again, my sincere thanks to all of you, including the teams that have organized this series of webinars. My best wishes to all of you. And with this, I would like to bring this webinar series to its closure. Thank you so much. Back to you.
For the wonderful speech and capturing the key aspects of the webinar series. With this, I just thank again the speakers today, Professor Ryota, Mr. Sintaro Fuji, and Professor Omar Abdulaziz for the presentation, taking the time. I also want to thank all the participants for taking the time out of their busy schedule for the webinar. And I then can conclude the session with the last comment is that you will get the feedback form. We request you to fill the form and provide us the information for better management of the future webinars. Thank you again. Have a safe day. Bye-bye.